with the pure iron, the elastic properties that we will get from the constraints of seismology show that the Earth's core should have contain several weight percent light elements, and people made a lot of progress on that, but still debating. And to me, that the one interesting aspect in providing additional evidence for this is that as the inner core precipitated, the light elements also fractionate between the outer core as well as the inner core, because they are two different phases. So that will likely generate the different chemical compositions between the Earth's outer core and Earth's inner core. So for that, I think nowadays people are still working on that, and including this work that Quan Zhang is going to lead, going to share some more details about the surface or the precipitation process of the Earth's inner core outer boundary. That will also help us to understand how the Earth inner core grow. So basically, that's a crystal growth in a very extreme condition. So with that, I just give very short, brief introduction. And for the rest of the discussion here, will be first presented by Quan Zhang, and then I think Brian will also have some comments later on. So Zhangquan, please move on.
Okay. Thank you, Professor. Hello, everyone. I'm Quan Zhang, and now I'd like to make a presentation on brief introduction to array method. Firstly, I must apologize that I feel a little bit sick after my graduation ceremony, because that's the hot and humid weather yesterday. So I actually did not finish reading this whole paper, which means that I'm afraid I cannot say something about the result and discussion part about the Nature Geoscience paper that my supervisor, Professor Yunfeng Chen, sent me several days ago. So, in the late talking, I would like to share what I have learned from this paper. So now let's get started. I would like to divide this presentation into three parts. And the first part is what is seismic array. The second part is why we would like to use seismic array. Finally, I will share the key idea from this Nature Geoscience paper named an initial map of fine scale heterogeneity in the Earth's inner core. Well, a seismic array is a set of seismometers deployed so that the characteristics of the seismic wave field at a reference point within or close to the array can be inferred by analyzing the waveform recorded at the different sites, which means that we regard the we deployed a lot of seismometers in such a small region could be regarded as an array. And a seismic array differs from a local network seismic stations mainly by the techniques used for data analysis. Thus, in principle, a network of seismic stations can be used as an array, and the data from an array can be analyzed as data from a network. Techniques are the key points to distinguish seismic array from traditional seismic station network. Based on array, researchers can make good use of different kinds of array methods, contributing to the development of array seismology. So please take a look at the right figure. This right station figure shows the Nature Geoscience paper using array method to measure the heterogeneity of the inner core. So in this part, I would like to talk about the two main types of array. Well, the first one is broadband array. The EarthScope program of US was going to deploy several stations from the West Coast to the East Coast in order to cover the mainland of the US and Alaska from 2004 to 2014. Well, the same as US Array, China has also held a program to establish China Array across China, China mainland. You may check the website for more information. And the broadband station has its characteristics like the frequency is almost larger than 0.01 hertz, and the spacing is often several kilometers to several tens of kilometers, as the data collecting period is often several months to several years. In addition, nodal seismic array are becoming more popular these years. Well, the left figure shows the map of deployment of nodal seismic array. In such a small region, you can see that maybe the latitude 2 degree multiplied to the longitude 2 degree. In such a small region, there are hundreds of seismometers, which means that the density of the stations is much larger than the broadband array. What's more, the ocean bottom nodal array is also designed these years. Different from the broadband array, the frequency is much higher than the cutoff frequency. You can see that the broadband seismic broadband stations has its cutoff frequency as 0.01. So that is much higher than the cutoff frequency of broadband stations. And the spacing is almost hundreds of meters to tens of hundreds of meters. As the collecting period is very short, several weeks to several months. So, take receive function method as an example. In my supervisor, Professor Chen, in his seismological research group, array method has been the main research direction of our group. Well, receive function, making use of the time shift between the P wave and P2 as converted wave, we could see that the teleseismic P wave converted to S wave, and there's a time, the velocity difference between the P wave and S wave, we can use this time shift to calculate the depths of MOHO or other interface like the MTZ. Well, in our research, array method has been added into a traditional workflow. For example, the wave field regularization by random transform and the interpolation by SSA, and other strategies, in order to let us know more about the structure as well. Well, another strategy, beamforming, enlarges the capability of the detecting the signals from the deep earth. So it is more likely a research technique, setting the back projected seismic arrays and finding the maximum value in the spectrum as the most possible point. And the figure from the paper is obtained by beamforming. You can see the darker the color, the larger the energy. So array method is a very good tool for us to know more about the deep earth. Not only beamforming for PK-IKP CODA, we will talk about the PK-IKP later, but also other ingenious methods are used for array seismology, enlarging our knowledge about the deep earth. For example, Zhi et al. Pay attention to the S-diff, which means that the S diffraction phase contributing to ultra low velocity zone imaging. And Frost et al. Use different kinds of PKP phase, like the PKP AB or BC or DF, to study the inner core anisotropy. So the figure 1A shows the seismic phase and their ray path. When there's a pair of events and the station, you can see this is the event and the station. The length of the great circle path is constant. You can see that the great circle is constant. If there's a scatterer inside the inner core, that is deeper than the inner core boundary. Look at this, deeper than the inner core boundary, the travel time will increase. In the figure, we can see that the yellow line is longer than the green one. So the slowness will be larger than the PK-IKP phase, which means that P means the P wave in mantle, and K means the P wave in outer core. The I means the K phase reflected on the surface of on the inner core boundary. So PK-IKP phase and the inner core scatterer phase will be seen in the PK-IKP coda. The star shows the epicenter of the events used. Since scattering wave could not be seen as a very strong peak in 20 to 100 seconds after PK-IKP phase, so they use a grid search strategy for the envelope of the waveform and get the peak energy as the resolved location of the scatterer. It has been marked in the black diamond like this. This figure shows 8 events in different location and incidence. The black points means the vertical incidence, and the blue ones marks the predicted slowness, and the 2 dashed circles represents the slowness of inner core and outer core boundary. This phase is just like this. You can see the 2 figures. I just make a screen capture from the Taupi script, and for the students who want to know more about the seismic phase, you can just download this JavaScript, and you can see that the different seismic waves, different seismic phase directly. And in addition, they use different time shifts to limit the depth information. In this figure, we can see the northwestern and southeastern part of the detectable region of LASA shows the high value, giving us more information of the scatterer's depths and width below the inner core boundary. So that's thanks for your listening. That's all for I have been learning. I have learned from this paper. So if you have any questions related to my please directly message me. Thank you.
Okay, thank you, Zhangjuan. Now, Brian, could you give some more comments and continue with the discussion?
Yeah, thanks, Chuan, for that presentation. So probably, as the rest of us here are not seismologists, and we're not well familiar with the techniques, I guess the main thing here is what are the results that came out from this study? Basically, what were they targeting? And so what they're targeting was trying to look at the heterogeneity in the inner core using these seismic observations, specifically from an array with a 200-kilometer aperture. And what they essentially found was, I guess, better resolved locations of scattering within the inner core than previous studies had shown. I think previous studies had basically resolved it down to hemispherical differences in velocity structure in the inner core, and that was basically it. So this allows to get a little bit better resolution between the inner core boundary down to the inner core boundary to 500 kilometers below that. So they essentially find a zone of strong scattering around the northeastern part of their resolvable area, and then also in the southwestern part. So that's essentially the main takeaway, is that they can get better resolution on at least the heterogeneity and scattering in the inner core, which is cool. And then they also present a hypothesis about how that could possibly form. And I think what they settled on was a hypothesis of fast crystallization, where there's a high flux, heat flux between the mantle and the core. And this is a flux of, I think, relatively colder material. And so that flux of cold material downwelling into the core could cause really fast crystallization. So you get a change in orientation of the crystals within the inner core, and that will give you a velocity anomaly, essentially. So when we looked at those plots of the slowness, it's essentially showing you the possible locations of these areas of fast crystallization. And I think that's the main physical takeaway from that paper, the Nat Geo paper. And then in the other paper with Science Advances, the Science Advances paper, they were looking at how this heterogeneity in the core, how that could possibly be related to observations of changing in the rotation rate of the core. So they basically use the same method as what was presented here. Well, the same array, but they focused on two explosion events around 1969 to 1975. Basically, they're able to solve for the rotation rate between the two pairs of events, and they saw a change in the rotation rate of the inner core. And so this goes against models where they say where the inner core is assumed to rotate steadily. And they basically relate the change in the rotation rate to oscillations of the inner core relative to the mantle, basically gravitational locking. So density variations in the mantle, you can think of it like tidal locking between the Earth and the Moon. We have density variations in the mantle will then lock with the inner core, such that the inner core will then oscillate. It'll change its rotation rate. And I guess the cool thing about that is that they can relate that change in rotation rate to a change in the length of day, which has some kind of periodic effect, about a 6-year period. So the two papers are, I guess, fairly connected in a way. They use the same array for their analysis. For this paper that Chuan was talking about, they used a lot more events, I think about maybe 70 events or so. And then in the later paper, they only used 2 events. But it's basically all about how do you resolve heterogeneity in the inner core, and how can you measure the rotation rate in the inner core using these seismological observations. So that was essentially my main takeaway as a non-seismologist, that they could resolve these things and confirm certain models with these new observations and with these new techniques. So yeah, Chuan, if you had anything else to add based on their techniques, like do you know if there's anything special that they're doing relative to what other people have tried to do in the past?
Well, actually, I just read this paper, well, 2 days ago, and I didn't finish, reading this paper. So maybe I will do more reading about the array method on, well, the inner core heterogeneity.
Yeah, one question I have for you is, do you know what is the effect of the aperture size on what you can resolve? Like you can have the very small aperture, right? The really dense nodal arrays, and that allows you to get greater than five hertz, I believe. But the one they're using here is a much larger one. And what is the trade-off? Why would one want to use a smaller array, and when would one want to use a larger array?
Well, from what I have learned, I think that the small range of array is often used in the deep Earth, well, the really deep Earth imaging, and widely used like the US array or China array is often used for the subsurface structures like the subductions or mantle transition zone like this. So it's just like two kinds of dimension of the deep Earth research.
Right. And with a smaller array, would you then only focus on a smaller area of the deep Earth? Like if you have this array in this papers with 200 kilometer aperture, so then they essentially cover what's shown here in this figure that you have up here, this North America, South America. So if the aperture was larger, would this resolvable area also be smaller?
Well, I've never thought about this question before.
Yeah, it's hard to know. We can ask Wei Wang in Wednesday. But yeah, that was a question I had in my mind, because they mentioned something about if you had a smaller dense aperture, you can resolve higher frequencies, and I wonder if those higher frequencies can give any extra information that they can't give here.
Yes. Okay, thanks for your comment.
Yeah.
I'm not a seismologist neither. I would like to say some of the comments that I didn't read as much details as both of you did. But to me, that there are some, according to results, some of the results, as John Chen mentioned earlier, people, that was also consistent with my memory. A couple of years ago, maybe 5-6 years ago, I heard Jessica Irving from Princeton back then. She was talking about the hemisphere heterogeneity of the Earth's inner core, and but she didn't went into too much details. I'm mainly talking about the north-south difference. But I think in this work that they, but actually my question is that how much better did people get on that? Is that the resolution improvement compared with this hemisphere heterogeneity? Has people improved that for the spatial resolution for 1 order of magnitude? Or
that's actually an interesting question, because there's a paragraph in the paper where they say their result does not match the previous hemisphere differences and anisotropy. And they didn't really go into too much explanation. So I'm guessing that's going to be a question reserved for Wednesday. What they did say, their results match better with attenuation studies, more recent attenuation studies that basically show somewhat similar structures, strong attenuation under South America and Western Asia. So yeah, but they say that it doesn't match the previous results. So I mean, they advertise it as having better resolution. So I assume you're going from a resolution of one hemisphere to another to something like, several 100-kilometer resolution. So that's probably at least 2 orders of magnitude better just from eyeballing it.
Okay, actually, that sounds a very large improvement. And then another thing is that, Brian, I don't know whether for this work, could they differentiate the effect of both temperature, which they try to explain using the cold flux to explain heterogeneity they observe. So could they differentiate the effects of temperature and composition? Because I don't think the inner core composition is homogeneous neither. But I
Right.
don't know whether this method is sensitive to that.
I don't think so. They basically mentioned that temperature could also be at play, and they don't really expand on that. So I think that's also a question that we'll have to ask him on Wednesday. Yeah, they don't go into trying to resolve or, trying to determine between those two effects. And I don't know if that can be determined purely from seismological observations.
Yeah, I guess he won't have a good explanation.
Yeah.
I think that probably will leave for some geodynamics and also people who are working on the inner core crystallization models on those, for example, this molecular dynamics or first principle calculations. I think those people probably will have better say on that. But I would be very interested to see. But another thing that jumped in my mind that is also related to the second part of the results is that the rotation rate between the inner core and outer core. So I remember that it was maybe it's almost 30 years ago, 27 years ago. So when Song Xiaodong was at Caltech back then, working with John Hamburger, and they discovered the rotation rate difference between Earth's inner core and outer core. Is that right? At that time, that made a big shot, and then people went on with the observation over the 2-3 decades and find that the difference might be positive or negative. So it's not necessarily one faster than the other. And this one that trying to, so this work, I think they only use a limited events, but they're trying to show or say that actually the rotational rate is not stable, and they gave her this locking explanation for that. So but as a non-seismologist, what I take the message from this is that this likely generates a chemical equilibrium at the inner core crystallization process, because people also I don't know whether they went into some more report about it, so that the inner core surface, when they grow from the precipitation of these metals from the liquid. So from liquid, the precipitation and solid, actually at the surface of the Earth inner core is quite a fluffy surface, is like snow. And of course, it's not a process, it's not filled by air, but filled by the outer core liquid. But the outer core liquid at the rotation has a very large stress, shear stress, as well as could tell, because the inner core surface is not smooth, or maybe people could not tell that. So, but if this is true as what they explained, I would expect that this crystallization process is not in the ideal chemical equilibrium as we will want, maybe. Well, that's just some of my wild thoughts. Yeah, I will leave time for other people to ask questions or comments.
Oh, just real quick to follow up on that. So are you saying the cold flux that they're explaining for the recrystallization, that sounds like a transient process and not something that would necessarily lead to an equilibrium in the chemical structure?
That's right. That's my interpretation.
Yeah, that makes sense too.
Yeah, because you have relatively colder part in Earth inner core, and then at a high temperature, it just leave it for like say 1 million years. I bet they, let's say that the temperature will reach re-equilibrate, and also all these elements. Now all the elements, their diffusion rates should be fast enough in the million-year scale to, or about hundreds of millions year scale to reach equilibrium in the end. But what we saw probably surface of Earth inner core surface is unstable. I say not unstable. I said not reaching the homogeneity, chemical equilibrium at the beginning. But I have another thing, that is that true that now seismology community that could resolve the topography of the inner core outer core boundary very well?
I'll have to ask Tuan for that. I don't know. They do reference it a bit, a couple of times in the paper. Well, I don't know if it's, I think they're mainly the topography of the outer core mantle boundary. I don't know if they've mentioned anything about the inner core, outer core topography.
So questions from our other participants or comments?
Yes, this is Ben. I'm a PhD student from Zhengzhou, and I have an unprofessional question, which is, so did the data in the, I mean, the seismic wave data in the geophysics and the data will, is these are same with the today? I mean, they are 40 or 50 years ago's data. And because in our geochemistry, we have a lot of improvements in the machine or the equipment, so we can get more precision data day by day. And so I wonder, in the geophysics, the data can be easily compared with today, since they use the 1970s data.
Well, good question. I think, well, the seismological researchers would like to use the new data for their research, but maybe for the typical, for the typical array or this, just like this research, they, there's no much data for them to use in their research. Like they just select 11, I think is 11 or more than 11 events, which is suitable for this research. So, well, if there's a new array or new data for the seismological research, I think we pretend to use the new data with good quality. So it just asks for the consistency, right? The consistency from the, well, of the previous research and the previous data and the data nowadays, maybe. Well, I think the seismic research will pay more attention to the just like the present, just in the deep earth, we regard the deep earth as the present condition. So I don't think maybe I have never thought about the change before, change in such a short period, like the 50 years could change the whole structure of the earth. So so maybe
yeah, Zhang Xuan, probably this is one exception we could have in the relatively short, even several decades of years, according to the research objects that we're talking about. Because actually for inner core outer core boundary, they did change in a couple of years because the precipitation rate is very fast. I think it's also the first author Wei Wang's work in PNAS maybe 7-8 years ago, that their work that trying to resolve that and showing that within, I'm not sure where this is work, where his advisor worked back then, that at USDC was that as the time goes by, even by years, you see the difference of inner core, outer core boundary. So this is one interesting exception when you talk about deep Earth, that the research object structure doesn't change within the very short time. But this one likely will change even in 30-year scale.
And another key factor for the paper on the oscillating of the inner core is that they used nuclear explosions, and we haven't had any of those recently, luckily. So probably this type of analysis won't be done in the future, and we can only use past data, and hopefully it stays that way.
Yes.
Yeah, I think people also studying for ULVZs, ultra low velocity zones, using the nuclear explosions back then in the Soviet Union. I think that's, yeah, people just going to use those data. That's something that only once in your lifetime, or what the people could got.
Okay,
That
thank
leads
you.
one more question related to that. They use vertical component seismometers. Is there a reason why vertical component is what they should use in this kind of study?
Well, and the seismic phase is PKIKP, which means that the the seismometers could the phase will be more clearer in a vertical component. So I think that's the main reason they use this.
Okay, yeah, that makes sense. Thanks. And do we have any other questions from anyone who took a look at the papers or from the presentation?
Okay, if not, then let's end our discussion today. So thank you very much, Zhangjuan, for leading the discussion. And thank you very much, Brian, for the comments and as well as the discussion. I really appreciate that. Let's waiting for the speaker on Wednesday. I think we already have some questions for him. So have a good evening, everyone. Have a good afternoon, Wumi. Okay, see you on Wednesday. Bye-bye.
Okay, see you.
See you.